I'll speak about the Diophantine exponents in the dimension 4. It's a joint work with Nikolai Mashuritin. It's unpublished yet, but we're looking forward to. Okay, let's start with the definitions. Some of them were mentioned yesterday by Nikolai Mashuritin and Leonard Zuner. So I'll repeat something. Let's theta be a vector and suppose that the components of the vector I independent with 1 over z over q. And we consider such a function psi of t. Let's draw a plot. It's very simple. Here is psi, here is t. It's almost everywhere. It's a constant, and it has leaps at the points which are the present approximations. We denote such points by q, and the value of the function we denote by zeta. q1, q2, and so on. And at this point, and so on. And now we consider two Diophantine exponents, omega and omega hat. Omega is called the ordinary Diophantine exponent, and omega hat is the ordinary exponent. It's clear that this inequality for omega hat, the left part is where because of the Dirichlet theorem, the right part is trivial. And we have the trivial inequality between omega and omega hat, the last line of the slide. And our goal is to prove some non-trivial estimates for I don't need it actually. What are the known results? The first is by Wojciech 60 years ago for the case n equals 2. And recently it's proved that the Yarnik result is the optimal one. Two years ago, Nikolai Mashuritin proved such an inequality for n equals 3. Another proof of this inequality was obtained by Schmidt and Leo Zumer, I think 1 year ago. We see that as the dimension grows, the inequalities are more and more complicated. And in our case, it will be also true. Now, some definitions I've told them. We consider the vector theta. And we can consider the sequence of best approximations zeta sub mu. And the values are, as it's written in the slide. What do we know about the vectors of best approximations zeta nu? We know that all these vectors cannot lie in a subspace of dimension 4. And also, Yarnik proved that there exist infinite many tuples with three consecutive vectors which are linearly independent. And I'll try to draw what the situation is. Here is the first vector. Here is the second, the third. Z sub mu plus 1, Z sub mu plus 2. This triple exists after Wojciech's lemma. And then the approximations start living in this two-dimensional space. They live, and sometimes we have another three-dimensional tuple. And once again, and sometimes we have a three-dimensional tuple such that, or this vector with this, and some previous vector, and this 1, 2, 3, 4, 5 are linear independent. This is this can be formulated. We formulated it in our proposition. You may see it's cumbersome or maybe even scary, but it's what I've said, but more formally. We have the treatise of vectors, and the situation continues infinitely many times. And what is the index of our theta? The index of our theta is the number of intermediate tuples of three linearly independent vectors. In our situations, the index equals 1. If we have another situation, 1, 2, 3, this is two-dimensional space, 1, 2, 3, this is another two-dimensional space, 1, 2, 3, and this, and one intermediate tuple and another intermediate tuple, the index equals 2. And here is the index of theta is our main concept. And now I'm going to formulate our results. We consider some polynomials, as it's written here. And all the polynomials have the property that they have the unique positive root, and the root increases to infinity as the parameter omega hat tends to 1. It holds for all the polynomials f sub 2, 1, f sub 2, 2, f sub 3, and f sub 1. And we denote the unique positive root of the polynomials by G1, G sub 2, 1, and so on. And here are our results. If index equals 1, we have the first inequality. And we have similar inequalities for the cases 2 and 3. And what can we say about the other cases? Our work required a lot of computation using special programs in or from Mathematica. And when the index grows, the complexity of computation also grow. And we decided that sometimes we have to stop. And we stopped for index equals 3. Because index equals 4 or 5, we do not have any new ideas in this case, so we decided to stop for the sorry. And the other thing I'm going to tell is about the optimality of these exponents. So we can't prove, but we believe that for the case 1 and 2, these exponents are, these estimates are optimal. But for the case 3, it's more complicated, but we can also calculate the optimal exponents, but we cannot prove. And now I'm going to tell something about the proofs of our results. We consider as 16-dimensional space. I'll tell you later why is it. And we consider the system of 15 inequalities. What do these inequalities mean? I'll show it for the first inequality, where psi sub nu minus 1 plus psi sub r sub 2 minus 1, and so on. What does it mean? This is just the fact that there exist 5 linearly independent best approximations. What does it mean? If we write a determinant, such a determinant, u1, u2, then u5. Since they are linearly independent and are integer, we should say it's greater or equals than 1. Now what can we do? What is z minus 1? Z minus 1. Q O, Q u1. That means that if theta is theta 1, theta 4, then theta 1 minus a sub u1 divided by u sub 1 is the best approximation. And the same is valid for B, C, and D. And if we can consider this determinant, this is the first line, the second line will be Q sub nu sub 2, and so on. And now we start to, we will substitute we'll subtract the first column from the second column with the coefficient theta 1 and so on. And what would we get? We would get the following determinant. And it will be something less than zeta nu1. So these values will be low. This is the key. And now we know that the determinant is greater than 1. Then we consider the biggest term in the sum of product. If we will write the determinant, and we take the logarithm of both parts. And here, what do we have? We have that it's greater than 0, and so on. There are other inequalities are obtained by the same method. And what do we have? We have a system of 15 inequalities and one equation. This equations means that these two vectors and these two vectors lie in common two-dimensional plane. And what is the lemma? The lemma says that if we consider alpha and g greater than 0, this system depends on alpha from the second line and g from the last line. And if the solution exists, then g is greater than g sub to 1 of alpha. I'll remind you what is g sub to 1 of alpha is the root of the polynomial f sub to 1. And we are looking for minimal g such that the system of the equation has a solution. How can we find it? This system of inequalities defines a cone in 16-dimensional space. We have a cone, and we have a hyperplane defined by the first equality. And what is the critical case where the system doesn't have some solutions anymore? For different g, we have different picture, but sometimes this plane contains the vertex of the cone. And this is the critical case. That's what we need. If we are in the vertex of the cone, that means that all inequalities turn into equalities. And we are lucky we have 15 equalities and 15 unknown variables. Now, so we can solve the equations, and we can express g via alpha. We can express, and we get that the g equals to g sub to 1 of alpha. And that's the proof of the lemma. And now I should say a few words. How do we deduce the main theorem from our lemma? If the index of theta equals 2, and we write all the conditions of the proposition 1 as inequalities on determinants, like it was written here. And now we can transform it into the conditions on the determinants with qi, where q are denominators of the best approximations, and with theta I, where theta are the values of best approximations. And it is, since the determinant is integer and non-zero, the biggest term is product of the determinant is bounded from 0, and that's what we need. So the system of inequalities for index equals 2 is very big. It contains about 25 inequalities, but we know what is the minimal g where it has the solutions. So some of the inequalities for such g turn into equalities, and some don't. And the computation were from Mathematica helped us to know which of the inequalities turn into equalities. And that's how we obtained the system of inequalities that's written in this slide. For index equals 3, we have another system of inequalities with even bigger dimension, but it's but it also can be solved with the same method. And what can be improved here? Of course, we can't calculate the uniform exponent for index equals 100 or 1000 and so on. So we need some new idea to how to calculate it for all indexes. Maybe it's there is a formula or so. And I think that's all. Any questions? Yes.
From the bound you gave, in which case do you get the sharpest bound for omega divided by omega half?
We didn't prove that the bound is sharp, but we believe that in the case 1 and 2, these bounds are sharp because of our calculations.
This was not the question. Comparing G1, G2, and G3, which gives the best, the sharpest bound for omega in terms of omega half?
The sharpest bound is for the first case.
Greater.
The first bound is greater.
Yeah.
Yes.
And the best? It depends on index. We can construct numerically a number with index equal to. So for this number, the is not first bound is not applicable as index equal to. We have only the second bound.
No, of course. But I was just wondering which one
Yes,
is the
it
greatest.
was, and this is a phenomenon.
Yeah.
That as it was, it means that the first bound is not optimal in general.
Okay.
As there exist numbers with exact second bound.
Of course.
But it is a numerical result. We didn't try to prove, as it is very complicated and cumbersome.
And also the second estimate is sharper than the third, and we believe that it continues.
And the third is worse than the second.
Yeah.
Any more questions? If not, let's try to meet you again.